Yes, it is. I've been trying to record them all, making sure I get them posted, but I don't always get them posted until later in the evening. So, but they're all getting posted. So if you missed a day for whatever reason, please make sure you check and see what we've done that day in class. I know they're terribly boring and awful to watch, but hey, that's what you got. So I'd say it's better than nothing, but it probably is not better than nothing. I've watched them. It's worse than nothing. So just not knowing what happened would probably be better for everybody, but that's not the way we do things here. All right, so today we are going to pick up right where we left off. You are going to have a quiz the last 10 minutes of class. So right at 10 o'clock, we are going to stop everything we're doing and you're going to have your quiz. So have that piece of paper ready to go. Number it 1 and 2, because there are 2 questions on your quiz. There will be a third too if we get far enough. So and make sure you're ready to go. Name on it and all that. Well, I don't care if your name's on it. You're going to be uploading it. So what do I care if your name's on it? Put your name on it anyways, just for fun, like real school, you know, period 2. Not that any of it matters. It doesn't matter, but we'll pretend it's like real school and just slide that sucker away. That way it will taunt you for the remainder of class, laughing at you, making you feel, you know, nervous and scared, all those great things. So today we're going to be talking about Hooke's law and elastic potential energy. We're going to do a couple of demonstrations and some stuff. So you will need a calculator today because you're going to be calculating some stuff. If you have one, a ruler would be helpful. A ruler would be helpful. I mean, it doesn't have to rule like measure something. It needs to be rule like straight edge, like that. You know, anything that can draw a straight line would be fantastic. So we talked yesterday a little bit about Hooke's law. Today, we're going to kind of really drive that home. So we're talking about elastic potential energy. And more importantly, Hooke's law. So let me switch over here. So yesterday we were talking about springs. We were talking about the fact that springs obey a principle, and that is that there is a restoring force. And I tried to talk to you about what the nature of that restoring force was. Today I want to kind of continue that. So we're going to draw kind of what I had yesterday, where I have a kind of a track and a backstop. And the reason I had to put a backstop there is, unlike kinetic energy, which we only need to worry about the object by itself, potential energies always are interactions. You're probably noticing that some of that in your homework. So let me clarify something. There is no gravitational potential energy for an object by itself, because an object by itself doesn't experience gravity. The only way an object experiences gravity is if it's near something else. So an object near the Earth experiences gravitational potential energy. So we state that the system, the Earth and the object together, store that energy. The same has to be said for a spring. A spring by itself can't store energy. It has to have something immobile that will allow the spring to either be stretched or compressed. And therefore, it interacts with its environment. So when we talk about springs or any form of potential energy, it must involve a system. So for, again, gravitational potential energy, that system is the Earth and the object. For elastic potential energy, it's likely going to be some form of backstop that allows the spring to interact with our object. I don't know what that backstop would be. A bow and arrow represents an elastic potential energy system. You provide both parts of the backstop. You hold the front end and you hold the string. So you're the one who is providing the backstop for the spring in that sense. For what we're going to see in the class, the backstop is this thing right here. We're going to use part of this track to hold the spring in place. So all forms of potential energy are an interaction with something else. Look for that, because I'm going to try and trick you into multiple choice. And there are tricks in your homework about this already. So we're going to talk today about Hooke's law. And Hooke's law pertains to what's called linear springs. And the word linear here does not mean that they have to be straight. That's not it at all. Linear means that the force from the spring is proportional to the displacement. This is what we talked about yesterday, that the force from the spring is proportional to the displacement. Now, Hooke's law has other things about it too. And I want to be really careful, because there's a lot of little details here, some of which are important, some of which aren't. So let me get all the details for you. First, force is a vector quantity. So let's put the bars above the top. Next, there is a linear function, which means K is a constant. That's what makes this linear. You do see that this is linear, right? You see the y equals mx plus b part of this, don't you? It's linear with no, y-intercept. There's got to be this negative sign here. This negative sign tells us that this is a restoring force. That's what the negative means. But if you just try to memorize that, you'll be wrong. The negative tells us that the force from the spring is in the opposite direction of its displacement. That's what the negative means. That if you pull outwards on a bow, the bow is trying to pull the string inwards. If you push inwards on a spring, the spring is going to try and push itself back outwards. The negative sign tries to restore the object to its original shape. That's what I want you to know when I say it's a restoring force. That negative sign is telling us that it's trying to restore the object to its original shape. That's what that negative means. X has to be the displacement, which means it's going to be measured as a length. And this is going to be a force, so it's going to be measured in newtons. This tells you that the spring constant is going to be in newtons per length. Generally, newtons per meter. Now, we're going to test this in just a second, meaning I want to conduct a quick experiment to determine the spring constant of a spring. To do so, we're going to use a simple lab technique, one I expect you to learn. That lab technique is linearization of data. And we've talked about this before. We're going to talk about linearization of data today, just for a brief moment, and I want to remind you of different ways we have to linearize data. The way I want you to learn today is the simple one. This is type 1, the simplest way to linearize data. We want to measure the spring constant, so we're going to start with Hooke's law. I'm stripping away the negative sign because we want to look at just the relationship between the variables, not the direction. So I've stripped away the negative sign and I've stripped away the vector symbols. So I can focus on just the relationship between the variables. Now, this has nothing to do with Hooke's law or with elastic potential energy. We're talking just about analyzing data. If you want to linearize data, one way to do so is to solve for the variable in question. So I'm going to solve for K. And when I do, I get F divided by X. In order to take a set of data and linearize it, this is telling me to plot this on the y-axis and this on the x-axis. We did this in a lab a while ago, but we just don't do as many labs as I'd like. If we do this, we should get a straight line graph where the slope would be the spring constant. That's what this is telling us. So we want to create the conditions where we can plot X, the displacement, on the x-axis, and force from the spring on the y-axis. This should give us a straight line plot. Now, to do that, I need to have a spring, and I need to have some way of measuring the force. So what we're going to do is pretty straightforward. I'm going to turn the camera so you guys can see this. So give me just one sec. You guys see my desk okay at home? All right. So we're going to use this car to, there we go, this car to measure the spring constant, because this is springy. And to measure the spring constant of the spring, I have a series of weights. I can't measure the force directly because I don't have a force probe that will measure a pushing force. I only have one where I can pull. We use that for the friction lab. But I do have weights that have a fixed amount on them. Like this one is 500 grams. So what's the weight of this if it's 500 grams? You need to convert it to kilograms and multiply by 9.8. So what's the weight of this? Hurry. Divide by 1,000, multiply by 9.8. Tell me it's 4.9.
4.9.
Thank you. This is 4.9 newtons. I've got two others that are 200 grams each. You know, divide by 1,000 gives you 0.2. 2 times 9.8, so 1.96. Got two of them that weigh 1.96. I can't measure the spring directly, but what I could do is I could put the weight on the spring and wait for it to come into equilibrium. When I do that, when it's in equilibrium, that suggests that the downward force from the weight is balanced by the upward force of the spring. Is that a pretty good way, a simple way for us to figure out what the force from the spring is then? So right now, the force from the spring is 4.9 newtons because I'm in equilibrium. And if I add 1.96 to that, I've now increased it to something, 6 point something. And I can increase it again. Got it? But we have to measure something else. We have to measure how far the spring also moved. So I've got a handy dandy one of these. Yeah, one of those, a ruler. And we're gonna measure how far the spring has been compressed each time. That way we will have a chart of force and displacement. Isn't that what we have to graph? We're gonna graph this today. We're gonna figure out the spring constant of the spring. We're doing this like a pretend lab where I take the data and you do the work. But it's only gonna be 3 pieces of data, so it should be pretty easy to do. Ready? All right. First piece of data, the spring and everything is 22 centimeters long. So when I put the weight on there, I'll measure how far it's moved, okay? So you guys at home, 22 centimeters. You guys, I hope you see that, kind of. Do you see that? Somebody at home say something because you're too far away for me to see your little faces.
Yes.
Hey, I got a yes. Woohoo! Here, I'll move the mic closer. That way I'm louder because that's what you need, louder me. All right, so we're going to put this weight on there first. I'm trying to make sure it's nice and in equilibrium. And I'm going to measure. And it went down almost, it's right at 20. It's right at 20. So I put 4.9 newtons on there, and the spring went from 22 to 20. All right, ready for the next measurement? All right, so I'm gonna put 4.9 and 1.96 together. How many newtons is that? All right, so the next is gonna be 6.86. Oops, make sure I don't get the catch on there. 6.86, and it went from 22 to 18.9. To 18.9. All right, ready to go for the next one? I'm adding another 1.96. So what's the total force now?
8.82.
What? 8.82. Wow. All right, here we go. I have to make sure it's not catching on anything or rubbing on anything. And it went from 22 to 17.9. All right. So give me 1 second. You now have a bunch of data, but I have none. So I'm going to need some of that data because I didn't write anything down. Do I look like a person who has a plan? All right, so we're back to work on this. We should now be able to construct a chart of data. And that data should have on it the force from the spring and the displacement. So let's go through and see if you can't tell me what all this data was. I remember one of them, 4.9 newtons. What was the displacement for that one? 2 centimeters. And then what was the next one? 6 point something? 6.89. 6.8 what? What was the displacement? 3.1. There we go. Nice and clear. And the last one was 8 point what? And the last displacement was what? All right, so we need to construct a graph because we want to find the slope of the data set. So I'm expecting you guys can do this better than I because you guys have lined paper. But then again, I saw some of your labs. They were not great. I'm going to, let's see, I have to have a graph that goes out to at least 4. So I'm going to go, let's see, 1, 2, 3, 4. I don't have a measuring device. You guys have rulers and such where you can measure. And I'm going to expect to see this graph on your papers here. So those of you who have sat back and are not doing this, be prepared. You're the one telling me the slope. And then I'm going to need to go all the way out to 9. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9. So all right, and that's going to be in newtons. This is unfortunately in centimeters. I'd like it to be in meters, so I'll have to convert that later. That's 1, 2, 3, 4. So, all right, I'm going to graph my data set, 4.9 and 2. .86 and 3.1. 8.82 and 4.1. That looks like my data set. I don't know what all you guys are doing. But that looks like what I have. And I kind of expect it to look like this. And I'll explain why in a minute. Yours should look something like this too. It shouldn't go through 0. And there's a good reason for this, which is why I want you to do it this. I want you to work the process. So you guys, I can't find the slope of mine. You guys have better tools. Having a ruler and a piece of paper, you have a much better way of finding the slope. Of course, if you really want to do this and find the slope easily, you can throw it right into the stat part of your calculator and do a Linearize on it. And it'll take you about 3 seconds for it to tell you what the slope is. So take a minute and get the slope. You're either going to find it from 2 points on your graph, or you're going to find it from your calculator. If you're going to find it from your graph, remember you're supposed to not use data points. You're supposed to only use something that's on your line. That's the way you're supposed to do this. But having done this lab before, I kind of know what to expect here for my data set because I measured this yesterday. So Adam's doing Linearize, or are you just doing it another way? Well, you put the left, you have to use 2 of your lists. Then you have to tell how to do it. I don't have a TI up here, so I'm not gonna do it. But I'm gonna wait just a short minute, and then I'm gonna call some folks out. We'll get 3 or 4 different people's slopes, and then we'll kind of come to a group consensus. Because we're gonna need it for your pop quiz, actually. Just coming up. You have an answer? Excellent. I'm sure I got a few more people. You have an answer too? Think so? People at home, I'm seeing if I got an answer from people at home. I think I got a few people with answers. All right. You guys at home, can you do me a real quick favor? Just in the chat, throw down your number. I'm going to walk the room in here real quick and see their numbers, and then we'll compare. That's the inverse of it, though. You have your X and Y. All right, so a lot of people have the exact same number, which means that's good news. That's nice and reassuring. There's a little variance around it, and then there's a few people who have the inverse. Let me just check the folks at home. All right, guys, I'm going to flip through here. All right, there's a lot of people who have 0.5. Let's talk about why you got 0.5. If you're using, just do a quick favor. In the participant window and at class, how have you did linreg? Just say yes in the participant window and raise your hand if you did linreg here in the class. Participant window. There's an awful lot of 0.5s. All right, because 0.5 is the inverse. You did run over rise if you got 0.5. So if you did linreg, you just put the lists in wrong. You did linreg probably L1, L2 when you should have done linreg L2, L1. It's that simple for linreg problems. But for our data set, it comes out around 2. And you should be able to see that it comes out around 2. Meaning when I look at my graph, when I go up to, from say here, I go up 2 and over 2, I go right around the 1. You see that? That's a rise over run of about 2. Definitely not 0.5. So you should be able to see your slope pretty easily. 1.87 is actually the most frequent number that you guys got in this class. And that's must be pretty close to being right. There's a little bit of variance because if you're doing this by hand, you are going to be kind of training yourself to try and line up your line with the data points, but there's going to be a little bit of dissonance. I do want to point out something incredibly important here. And if you're really paying attention to this, it will help you on the exam. You can't just take a single number and divide. If you look at these two, if you take 4.9 and divide by 2, you'll get 2.5, which is much bigger than if you take the next two numbers and divide, and the next two numbers and divide. The reason for that is because there is a clear y-intercept in all of your data. You guys do see that, right? And we don't expect one. I mean, we don't expect a y-intercept. That's because this is a real spring, not an ideal spring. Hooke's law is an ideal condition, but we have real springs. Real springs have coils that touch each other. Real springs aren't perfectly linear. It takes something to get them started. And then once they're started, they usually are linear. But it takes something in the beginning to get them started, which is why you have to graph the data and do this, because you have to get rid of that y-intercept and get beyond it so you can get to the slope, which is why you just can't take two numbers and divide them. This is why we need a set of data. Now, we have a set of data. And for the next few moments, what I would really like to do is focus on people who are really mathy. And I don't know how many of you are actually mathy, but there's probably a few of you who are pretty mathy students. I want to just go ahead and make this a little straightforward. You got 1.87, so 1.78. Let's just go with 2. That okay with all of you? And this is 2 newtons per centimeter. Newtons are on the y-axis, centimeters are on the x-axis. This is our spring constant. But generally, we put our spring constants in newtons per meter. So we need to convert this into meters. I'm going to use a unit multiplier with centimeters on the top and meters on the bottom, which I'll put a 1 here and a 100 there, which gives me 200, which is all, my head's like totally in the way. So that's not helping at all. And nobody wants to see that anyway, so let's just fade that out. 200 newtons per meter. This is the spring constant we're going to use today. Now, just let's put this into perspective. Spring constants are usually big numbers. It is not uncommon for your spring constant to be in the thousands or the 10,000s. So having one in the hundreds for a little toy car, that's appropriate. I want you to think, this says that it would take 200 newtons to compress it a meter. The spring probably can't even stretch that far, but that's the unit we're using. So generally, you tend to see really big numbers here because springs don't stretch very much. And that's why we tend to see big numbers, because it takes a lot of force to stretch them a lot. So the springs on your car that hold the car up and allow it to kind of bounce with the road, those are probably hundreds of thousands of newtons per meter, because they don't ever stretch more than a couple of centimeters, and they can hold thousands of pounds. So we tend to think of spring constants, and we expect to see spring constants be a big number. If you get a spring constant that's small, like 5, that seems irregularly small. You know, this one you can easily push with your hand, and it's still 200 newtons per meter. And this is all based on our data. It's not like we made this stuff up. So newtons per meter, that's our typical spring constant. Now, here's the thing I want to talk to you about. It's not about Hooke's law. It's about the fact that springs can store energy. That part shouldn't be a real surprise. In fact, let's take a look at something for just a minute. This is another kind of quick demo. So I'm going to swipe over here, make you guys look over here. And I'm not going to take the chroma keying off, because it's only going to take a second. But this car, I can push the spring in, and it can be held in place. And when I want, I can trigger it. Clearly, there's energy stored in the spring, because right now, the system has no energy, or appears to have no energy. And when I trigger it, suddenly energy comes from somewhere. Well, there was energy before. When I compressed the spring, I did work on the spring. There's a little hook in there. That hook is holding the spring in place. So now this system has stored energy. Another form of potential energy known as elastic potential energy. And that energy is stored in the spring. This is how a bow works. This is how a lot of those little toys you guys play with work, pinball machines, but not roller coasters. Roller coasters don't shoot you off using a spring. We'll talk about why in a few seconds, but this is another form of potential energy. And it's called, again, elastic potential energy. Now, this is just adding to our lists of energies, because we have, so far a couple lists going on. We have gravitational potential energy, mg h minus h naught. We have kinetic energy, which is 1/2 mv squared. And now we have a new one we're going to call elastic potential energy. Unfortunately, to get elastic potential energy, we have to do work compressing a spring, but that's a problem. And the problem comes from the fact that when we do work, we have to use information about the force. If you'll remember, work is force times distance times the cosine of the angle. Now, look, I really want to speak to the math folks, but everybody must hear this. This definition of work assumes our force is constant. But we have a formula for force that shows that it's not constant, that the more you change X, the bigger the force has to be. But we are trying to change X. We're trying to push against the spring, which means the bigger X is going to be, the more the force changes. We can't calculate work using this because it's just not going to work. It's going to take calculus to do that. And since most of you aren't in calculus, it's going to be hard for us to come up with an expression for the work. On the other hand, and this is important for all of you, we have a graph. I've told you before that there's information contained in graphs, and you should always look at the meaning of the slope and the meaning of the area for the graph. Now, you might not believe this, but the slope we already know. If you have a force versus position graph, the slope is the spring constant. We just did that. We created this graph for the express purpose of finding the spring constant. But if you look at the area of this graph, the area is going to be force times distance. You see that, right? We've talked about areas of graphs before and trying to find their meaning. But if you have a force versus position graph, the area under the graph is the work done. And yes, I'll expect you to be able to do that on a test. Multiple choice, give you a force versus position graph, and you tell me how much work is done. I definitely expect that. Now, for the next few moments, I want to talk just to the math kids. You guys who are not super mathy, you can fade away for a minute and come back when I make my grand summation at the end. So right now I'm just talking to the super math kids because this is going to be a little boring. Look, super math kids, we're going to find out what the elastic potential energy using a form of calculus, but we'll call this like pre-calculus. We don't really have that class so much anymore, but we'll call this pre-calculus. We can find the area of this graph, and we can find an expression for the area of this graph. The first thing we have to do is we have to make this an ideal spring, which means we have to cut away that y-intercept and reset our x-axis to be here, where that white line is. Because real springs have this y-intercept, but don't actually store the energy in here, because this part of the graph is actually where the spring is, the coils are touching. There's no energy stored here. I don't want to explain that as to why that is. You just have to believe that that's true. We're going to deal with the ideal part of our spring, which is the kx part. Now, I'll remind you that if I ignore that bottom piece, this is a triangle whose area is 1/2 base times height. The base of our triangle is the displacement. So I can write that as x. The height of our triangle isn't unknown to us because the height of our triangle is the force. So I could write this as x times F, but our force depends on x. Meaning if I wanted to find, say, the height that goes with this point on the graph, then to find this height, this position on the graph, I would substitute in kx to find out what the size of that force is. So the area under the graph between 0 and x ends up being 1/2 kx squared. This is how you calculate elastic potential energy. All right, all the people who aren't math geeks, come back. That's the final part. You need to know that. That's our third form of energy, elastic potential energy, and it comes right from the area under the graph. So we now have 3 forms of energy: gravitational potential, kinetic, and elastic potential. Now, with that being said, it behaves just like every other form of energy. when you're asking yourself whether you think the cart has elastic potential energy, you add one more question to your list of questions. Those questions were, does the object change height? Does the object have velocity? Is the object pushing against a spring? Just add a new question. That question tells you whether it has elastic potential energy or not. So here's your quiz, because I did not forget, and it's 10 o'clock. I'm going to take the cart, and I'm going to compress the spring. When I compress the spring, I'm going to shoot the cart forwards. So the cart here is going to have the spring compressed. I'm going to release the spring, shooting the cart forwards, where the cart will roll up until it finally comes to rest. I would like the maximum height attained by the cart. I'd like the maximum speed attained by the cart. The cart has a mass of 125 grams. Just so you know, that's 0.125 kilograms. And over here. There we go. While I'm holding the cart, I'm going to measure how far the spring can be compressed. Well, it looks to me like it goes from 5 to 0.5. So how far is the spring compressed? That's right, we compressed the spring 4.5 centimeters, which of course, I'm sure all of you remembered, put that in meters. And our spring constant is 200 newtons per meter. I think I've given you all the information you need to be able to tell me how fast the cart goes and how high the cart goes. So that's your quiz. I would like to know the maximum speed of the cart and the maximum height of the cart. You've got 5 minutes. Hurry. So again, just to make sure we have this, when we release that, it goes up to about where that hook is. And when we're looking at how much, our value should be in agreement with this, well, I can't imagine it's more than a meter or two per second, and it's not going much more than 20 centimeters or less above its lowest point. So when we look at your answers, that's what we expect to see. So looking at the math of it, for those of you having difficulty, and there's a few of you, at the bottom, it's all elastic potential energy. Now, the moment it's released, all that energy has become kinetic. Now, you could argue that there's a little bit of gravitational potential. There's just no way for us to measure how high the cart went when the spring was right here compared to when it was right there. That's just not much of a change in height. So let's assume that Vmax is when all the energy is kinetic. And the maximum height is going to be when all that energy is gravitational. But the energy should stay constant the whole time since there's nothing to take the energy away. So the energy here should be equal to the energy there. And these two should also be equal. They should all be equal. So in looking for what I'd expect you to do here, I'd expect you to say that, well, 1/2 kx squared has to equal 1/2 mv squared, which also has to equal mg h minus h naught. This is the top, this is fastest, this is the bottom. Conservation of energy says the energy stays the same. 1/2 times 200 times 0.045 squared. We know how much energy was in the spring. We measured the spring constant, we compressed the spring. This is how much energy is in the spring. It's not very much, right? Like 0.2 joules. What do you get, Tanner? Because I know you wrote it down. 0.2025 joules. This is the amount of energy we have. The fastest the car could go then would be 1/2 times 0.125, because that's the mass of the car, times v squared. Now, a lot of you have this written down, but you don't have the right answer. You solve that for v, you get 1.8 meters per second. That's v max. 1.8 meters per second. At the same time, I can set this equal to m g h. I'm going to assume that h naught is 0. How high does it go? Same amount of energy, 0.2025. Solve that for h, you get about 16 centimeters. This is not your quiz tomorrow. Because here's the thing. When I actually go over here and measure how high the car went, that's 13 centimeters, not 16. Why is it 13 centimeters and not 16? Go ahead. Yeah, I would say probably there's friction. And there's not just friction. Did you hear the cart? So some of the energy was converted to sound. And also, we haven't talked about this, but the wheels are spinning. That's another form of energy we haven't even discussed. We assume the car's sliding, but it's not. It's got parts that are rolling. There's other places the energy is going, and we're not accounting for it all. This is how much energy we think the cart should have. But at the end of the day, the cart actually had this amount of gravitational potential energy at the top. But it started with this amount of energy at the bottom. This is the energy at the beginning. This is the energy at the end. These are actual values. We know, we measured them, suggesting that there is some missing energy. You should not just be able to solve for how much energy we expect to see in the system, but if given an alternate on what actually happened, you should be able to tell me how much energy was lost, how much energy was converted to some form of internal energy, heat due to friction, sound, things like that. And you would do so by comparing the expected amount of energy to the actual amount of energy you have. That's what I would expect you to be able to do tomorrow. Yes, sir.
So when you subtract the actual, the ideal to the actual energy, it looks like you get like a 0.04 or whatever. What is that energy? Like, what would you label that as?
There's a lot of ways we can describe that energy. If the problem were to say how much work was done by friction, then they want to direct you to say that that was the work done by friction, and that's what you would say, work done by friction. But the truth is, that's a cop-out. That although I'm sure friction took some of that energy, there's other forms of it too. Like I said, we can hear it. So we know that's some of the energy too. We tend to describe all of this as some form of internal energy. So we might say delta U, because U is the term we tend to use for energy, and we put INT for internal energy. So there's some energy converted into some form of internal energy within the system. Does that make sense to all of you? Because this is in your homework too. And so I'm expecting that if you're working on your homework, you should be seeing some of these kinds of questions talking about losses of energy to the environment. So conservation of energy is an ideal circumstance. And what I want to finish off by saying, and let me turn this around so that I'm back here. Not that you all need to see me, but I'm trying to make my point. There we go. So let me make my point. Oh, there's no announcements. Weird. So what I'm trying to say is energy is conserved, but sometimes we don't know where it goes. You have to be ready to understand that sometimes the energy gets transformed into something internal to the system. And that's the point. All right, guys, that's all for today. Please have a fantastic day.